Imagine a helicopter soaring through the sky, its powerful engine propelling the rotor blades that keep it aloft. Now picture this, the engine suddenly fails. This is where the remarkable capability of autorotation swoops in to save the day. Autorotation allows a helicopter to make a safe landing even when the engine is no longer supplying power to the main rotor. Think of it as a controlled descent, a carefully orchestrated glide back to Earth. It is a critical skill for all helicopter pilots. A life-saving technique that transforms a potentially catastrophic situation into a manageable one. Just like a parachute for a skydiver, autorotation is a helicopter's backup plan, its safety net in the sky. It's a dance between gravity and lift, a delicate balance that pilots train rigorously to achieve. At the heart of the autorotation mechanism lies a crucial component known as the freewheeling unit. This ingenious device, often described as a one-way clutch, allows the main rotor to continue spinning freely even when the engine is no longer driving it. Think of the freewheeling unit as a bicycle's freewheel. When you stop pedaling a bicycle, the freewheel allows the rear wheel to continue spinning, even though the pedals are stationary. Similarly, when a helicopter's engine fails, the freewheeling unit disconnects the engine from the main rotor, allowing the rotor to spin freely. This disconnection prevents the drag from the engine from slowing down the rotor. The freewheeling unit ensures that the rotor remains a source of lift even without engine power. To truly grasp the magic of autorotation, we need to understand how airflow over the rotor blades differs during powered flight and autorotation. In powered flight, the engine drives the rotor blades, forcing air downwards and generating lift. In autorotation, however, the airflow is reversed. Because the helicopter is descending, air flows upwards through the rotor system, from the bottom of the rotor disc to the top. This upward flow of air keeps the rotor blades spinning, much like how wind spins a pinwheel. This change in airflow direction is crucial for autorotation. As air flows upward through the rotor disc, it interacts with the rotor blades at an angle. This angle of attack generates the lift needed to keep the helicopter aloft. The pilot controls the angle of attack by adjusting the pitch of the rotor blades using the collective control. Section 4. Vertical autorotation, descending safely from the sky. Imagine a helicopter hovering motionless in the sky, its engine humming steadily. Suddenly the engine sputters and dies. This is where the skill of performing a vertical autorotation becomes paramount. In a vertical autorotation, the helicopter descends straight down like a feather falling from the sky. The pilot's primary objective is to control the rate of descent and ensure a soft landing. This is achieved by manipulating the collective and cyclic controls to manage the airflow through the rotor system. By lowering the collective, the pilot reduces lift and initiates a controlled descent. By making subtle adjustments to the cyclic, the pilot can keep the helicopter level and prevent it from spinning. Section 5. Rotor blade regions, driven, driving, and stall. As a helicopter descends in autorotation, its rotor blades are not spinning uniformly. Different sections of the blades experience different aerodynamic forces, leading to the formation of distinct regions: the driven region, the driving region, and the stall region. The driven region, located at the rear portion of the rotor disc, is where the airflow is moving faster than the rotational speed of the blades. The driving region, located at the front and outer portion of the rotor disc, is where the airflow is moving slower than the rotational speed of the blades. Here, the blades are essentially plowing through the air, generating the majority of the lift required for autorotation. The stall region, located at the inner portion of the rotor disc, is where the airflow is highly turbulent, and the blades are operating at very high angles of attack. This region is prone to stalling, which is a loss of lift due to the airflow separating from the blade surface. The stall region generates very little lift and can be a source of drag. Section 6. Understanding force vectors and equilibrium. To understand how a helicopter maintains a stable autorotation, we need to consider the various forces acting on the rotor blades and how they interact. These forces can be represented as vectors, which are arrows that indicate both the magnitude and direction of the force. One of the primary forces at play is lift, which acts perpendicular to the rotor blade's direction of motion. Lift is generated due to the difference in air pressure above and below the blade, a result of the blade's angle of attack. Opposing lift is drag, which acts parallel to the blade's direction of motion. Drag is the aerodynamic resistance that opposes the motion of the blade through the air. In addition to lift and drag, we also need to consider the force of gravity, which acts downwards on the entire helicopter, and the centrifugal force, which acts outwards from the center of rotation. Centrifugal force keeps the blades extended outward during rotation, similar to how a ball on a string stays extended when you swing it in a circle. During a stable autorotation, these forces are in a state of equilibrium. Section 7. Mastering autorotation pitch, descent rate, and rotor RPM. Mastering autorotation involves understanding the delicate interplay between pitch, descent rate, and rotor RPM, which stands for revolutions per minute. These three factors are interconnected and must be carefully managed by the pilot to achieve a safe and controlled descent. The pitch of the rotor blades, controlled by the collective, determines the amount of lift generated. Increasing the pitch will increase lift, slowing the descent rate or even allowing for a climb. Conversely, decreasing the pitch will reduce lift, resulting in a faster descent. The descent rate is the speed at which the helicopter is descending vertically. It is influenced by the pitch of the rotor blades, the helicopter's weight, and the density altitude. A higher descent rate will result in a greater airflow through the rotor system, which can be used to increase rotor RPM. Maintaining a specific rotor RPM range is crucial for successful autorotation. The pilot controls the helicopter's descent rate and rotor RPM primarily through the collective and cyclic controls.